So our second panel is on water efficiency, vulnerability, and critical needs. And I am going to introduce the moderator of this panel, Elissa Yates. Elissa is a research hydraulic engineer at the U.S. Army Corps of Engineers Coastal and Hydraulics Laboratory in Vicksburg, Mississippi. She's been with the Corps for 6 years, and her research has included the development of continental scale stream flow forecasting applications, quantification of societal benefits for flood risk management, and examination of hydrological variability as a driver of conflict and adaptation worldwide. She currently serves as the lead for the development of the forecast-informed reservoir operations screening process. And she holds a BA in Economics and Humanities and a BS in Civil Engineering from the University of Texas at Austin, and a Master of Science in Civil Engineering from Mississippi State University. So please join me in welcoming Elissa Yates.
Thank you, Anna. That was such a great panel this morning. Good job to all the panelists and moderator Rob. I think that set such a good tone for the rest of the discussion, this broader context of the issues that you guys are facing and the thinking toward how to address those issues. I'm excited for this panel to be getting more into, I think Chuck put it, the sciencey researchy things, but still with a heavy emphasis on how to translate all of that science research and information into action and improvement to address these major challenges. So as Anna mentioned, I'm traveling here from Vicksburg, Mississippi. This is only my second time ever in Colorado and my first time to the Yampa, and I'm just bowled over by the beauty of the region. And it's great to be here with all of these people who are so focused on stewardship of the land and addressing these issues. I'm just very impressed with this group and hope I get to come back many more times. So thank you for having me. So we'll have 3 speakers for this panel. First up will be Dr. Keith Musselman. Oh, okay, you're on deck, you're ready. Okay, so Keith is coming from UC Boulder and INSTAR, which is the Institute of Arctic and Alpine Research. He's a hydrologist who conducts research on land, water, atmosphere interactions, including snow, runoff production, forest hydrology, and remote sensing. I also looked at your website and noticed that last year you won an award for outstanding mentorship of undergraduates. So that's a very cool accomplishment, and we're excited to hear from Keith. So go ahead and have you up. And we'll have a similar structure to the first panel where each speaker will speak for about 15 minutes, and then we'll have a few minutes dedicated to Q&A for that speaker, and then reserve about 20 minutes at the end for a broader discussion with all 3 of our panelists.
Thanks, Alyssa, and thanks, everybody. I think it's safe to say that we hold similar values in this room regarding a landscape that looks like this and some of our headwaters. This is a assemblage of 3 different photos of the San Juans. This is the Center for Quebec Basin, a research site for snow and avalanche studies. And this is put together by Jeff Dees, who's in Sticky Farms, Snow Observatory Incorporated, as well as Matthew Kennedy, who is an Oscar-nominated documentary filmmaker who made Chasing Ice. But this is just an assemblage of from a time-lapse photo, a camera pointed at this basin, and I just grabbed a mid-winter, a spring, and a summer. And there's something beautifully complex about this landscape. From a science perspective, from a public values perspective, and I could spend all day thinking and talking about the processes related to wind and precipitation, how weather and landscape interact to create the resource that we're so heavily reliant on and talking about today. And as scientists, water scientists, so we put out weather stations to monitor, and this monitoring is critically important to be able to both understand that complexity and to be able to translate it into information that is usable to the community. But they're often at these single little locations and often at great expense to maintain this over a long period of record. So we face challenges to be able to expand over something like the Colorado River Basin or the Yampa Basin. And increasingly, we're reliant upon advances in numerical modeling that can make that leap to spatial scale. And I'm moved by a recent paper by Jessica Lundquist at the University of Washington, Anthony Gutman at NCAR, Mimi Hughes at NOAA, and Sarah Kapnick, who was recently appointed Chief Science Officer for NOAA. And what they've proposed is that our skill in modeling, using things like regional climate modeling and high resolution, have now bypassed the skill of our observation networks to monitor, for example, precipitation. And that's really exciting. It's kind of an advance in the field, but both from the perspective of the science that we're doing, the atmospheric sciences, but also the numerical computing technology that is advancing alongside it. And this animation here by Ethan Gutman at NCAR, the National Center for Atmospheric Research, is a loop of a high resolution simulation over the US. And this is showing cloud, this is vapor, but you can imagine this being similar to cloud development over the course of the day. That pulsing that we're seeing is the representation of clouds and vapor enhancement. At the same time, we need to be able to ground these models to observation. So that can be improving the simulations based on nudging or data assimilation. And so this empirical observations is critical to maintain. So I just wanted to give a couple of examples of how we use both models and measurements to understand the state of our systems. This is a paper that was published last year by myself and colleagues, including Julie Dano, who's the Aspen Global Change Institute Research Director, and is sitting here today. We looked at snow telemetry sites, SNOTEL, but also some other stations in Canada that are similar, that weigh the overlying snowpack and have done so since, in some cases, going back to the early 80s. And so when we look at those records, we can look back and see how has snowpack changed. And if you look at the frequency of winter melt, the graph on the left shows all red stations that have a statistical increase in winter melt, more frequent winter melt. Things are changing in the winter. If you compare that to the graph on the right, which is how many of those stations have reduced snowpack, and it's a much lower number of stations, which is to say that there's this interannual variability that I think we saw with the precipitation graphs in the earlier panel, that is a noise, and underneath that noise there is this trend. And so it sometimes takes these observations plus the model to understand where is the signal that we're looking for, where is that anthropogenic forcing. And so this paper we titled "Winter Melt Trends Portend a Widespread Decline in Snowwater Resources," that we haven't started to see yet in the record, but as an indicator, as winter melt starts to increase, that eventually we'll start to see snowpack declines become much more widespread. We can use those high resolution models to do climate change simulation to see how conditions will change this century. In this case, this is a business as usual emission scenario for the end of the century to understand how rain on snow flood risk might change. So this is taking the top 10 largest rain on snow flood events for each of these large basins for a historical period, and then comparing that to a future period. And if you look at the total volume of water produced by those top 10 events on the left, that's a map that lights up green if there are increases and brown if there are decreases. And I think one of the things to point out is that there are places that are brown and places that are green. The Pacific Northwest, for example, a place where the models project there to be less rain on snow. And that is because in the future climate there is less snow. So again, another example of beautiful complexity in trying to understand how emissions are going to change our environment. Also, the risk that we face. How are those events changing? It's interesting to break that down, and the map in the middle shows changes in the percentage of the spatial extent of rain on snow within those basins. And on the right is the intensity of those storms. And what the models are suggesting is it's not necessarily the intensity of those rain on snow events that's going to change. It's the spatial extent, which is to say there's something quite interesting about when a rain on snow event occurs. that it's limited to generally a lower elevation and middle elevation range where rain is falling on snowpack. In the future climate, the models think that we're going to see rain to the summits in the winter and the spring that we haven't seen historically, and particularly that lights up places like the Sierra Nevada. It lights up places like Utah, Colorado, and in terms of the increase in the volume of water produced by these events. In some cases, the darker greens are more than 100% increase. Now, there's also, we're at risk of changes in that the flood risk, but also the water quality. So what does it mean to have increasing winter runoff events? For a place where historically we think about the ground being frozen, not much water moving in our rivers, what does it mean for water quality if suddenly our rivers are flowing in the winter? And so this is a study that has just been accepted and is impressive with environmental research letters to understand how our rain on snow events overlap soil and nitrogen, soil and nitrogen and phosphorus stores in the US. And we showed that 50% of the US stores of these nutrients are at risk of being flushed at a time where we hadn't seen that historically. And I'm just stepping back to kind of the theory of change and thinking from a hydrologist, what's unique about snowmelt and runoff production as it relates to water resources? And I always like to make the point that snowmelt magnitude and the persistence of that snowmelt during the spring season is unlike that of rainfall. And an example that I give is the annual snowmelt pulse. So this is taking a SNOTEL site, a telemetry station from above Boulder, Colorado, in the Continental Divide. And if you look at the long-term average maximum snow water equivalent of 19 inches that occurs right around May 1st. And then look at the number of days it takes on average for that to melt out, just about 45 days, about 19 inches of SWE. And then if you pull up a depth, duration, frequency curve to understand what would the rainfall event be? How many years would you have to wait for a rainfall event of that magnitude to occur? You max out to about 100 years. So that is to say that the annual snowmelt pulse is equivalent to the 100-year rainfall event. It's pretty unique. So the snowmelt magnitude that happens every year is unlike that of rainfall. And at the same time, snowmelt is an efficient runoff generation mechanism. And this is a study by Dongyu Li and co-authors from 2017. And they looked at the Western US and they ran this unique hydrological model that was able to track water that came from snow versus water that came from rain. And that told them the fraction of stream flow that was occurring from snow versus rain. Now, one of the things to highlight here is that the mountain ranges are lit up. That makes sense. 25% of the Western US produces 90% of the stream flow. And these are our water towers. They dug a little deeper and plotted those colors, this fraction of snow, stream flow of snow on the y-axis, and on the x-axis, the fraction of precipitation of snow. Now, if rainfall and snowmelt produce the same amount of runoff, all of dots are lined right up on that one-to-one line, that black line, but it doesn't. So on the y-axis, the model is saying that snow is much more efficient at generating runoff than the equivalent rainfall. So what does this mean for a warmer climate where we have less snowfall, less snowmelt, and more rain? And this is consistent with current academic thought about what the future will look like, that a precipitation shift from snowfall towards rain will in and of itself decrease stream flow. What's not agreed upon is the mechanism. So why is snowmelt more efficient than rain at generating runoff? And there are a couple of plausible explanations that go back to basic hydrology and physical principles. One is that snowmelt occurs when evapotranspiration, the use of water by plants and evaporation to the atmosphere is relatively low. Whereas summer rainfall is more prone to evapotranspiration. And the second is that persistent snowmelt, that 19 inches, for example, occurring over 45 days, more readily connects hill slopes to shallow groundwater reservoirs and to streams. You know, I've always been moved by this quote. This could have been said by anybody in the last couple of decades at a meeting such as this. We know more about the movement of celestial bodies than about the soil underfoot. But it was said by Leonardo da Vinci in the 1500s. And I think it's still true today. And 500 years later, scientists are focused on what we're calling the critical zone. So it's become an international initiative to understand more about how the plumbing of our landscape. How does stream flow originate? And how can we better understand what's happening underneath our feet as it relates to water resources? So I just think that we're at an exciting scientific frontier right now, at the intersection of climate modeling, of computer science, of remote sensing, of geophysics, of ecology and hydrology. And I think a number of people today are going to talk about the need and the exciting advances in observation as well as modeling. So I'd ask, underline the forefront question: how are we as a community observing changes in our water cycle and working to build resilience in the face of these changes? And that requires understanding and addressing the beautiful complexity of the system. And I'd state that to do that, we can't be working independently. So we need to break down this idea of an ivory tower, but let's be honest, and professors don't make that much money, so maybe it's a silo. So I think we need to break that down and move towards this idea of transdisciplinary community efforts to address societal impacts using societally attuned efforts towards convergence. And I'll mention a little bit what I mean by convergence. So the National Science Foundation, as earmarked in congressional legislature, is working to improve convergence. And examples of convergence are moving away from working within your single discipline towards communicating insights to other disciplines and groups. And if you think about on this convergence ladder in the colors as the status quo, we can make improvements, and we have over the last 100 years made improvements on the status quo. Working towards expanding that status quo, expanding what we're capable of doing by working across disciplines and starting to create new frameworks and languages to understand and solve complex problems. And I think that's exactly where we're trying to get to, and eventually disrupting. We're trying to disrupt the status quo. We need to address the pressing challenges that population pressures and climate change are having on us. And that requires convergence, that productive convergent teams greater than the sum of their individual parts, and deep convergence, breakthroughs and insights with solutions that were not possible previously. And one example I'd give of a convergence science is the advent of digital printing of human organs. You can imagine the teams of scientists and engineers required to be able to print and to successfully transplant hearts, lungs, livers into humans. And that's being done. Can we do it? Yeah, we can do it. I'd say the same thing about climate change and water issues in the West. Can we do it? Yeah, we can, but it's going to take us as a community. And it's an international community. So in the interest of time, I just wanted to leave up the take-home message and state that actionable climate services to inform adaptation, to planning, to advocacy require new strategies and convergence efforts on behalf of science, but also resource managers and particularly funding agencies in the US. Funding agencies need to be able to look at the grassroots, at organizations such as this, all the way up to the largest institutes in our country to be able to make these advances. Thanks.
Not on the road. Thank you. That was fantastic. And I wasn't trying to prompt you this time, I was actually just scratching my chin, but you're right on. So we have a few minutes for questions directly to Dr. Musselman, and then we'll move on to our next panelist. So we've got a question here in the back. I will for your microphone.
Great talk. This is Ian McCarthy from the Jet Propulsion Laboratory. So people out here. I wanted to ask you about your snow rain slide. In particular, you had a couple of information there. That was a great slide. There seemed to be one part missing from the phase transition from solid to water to liquid to vapor. And so, do you want to comment? Is that part of that play? And that's a pretty complicated slide. And I don't realize that this is maybe focused on that point, but that seems to be a big part of that as well.
Yeah, thanks. That's a great question. I think that's one of the complexities of the climate and the interface that we're studying, and that you yourself studying those. And it's one of the things that we're seeing that these research models can be better at high resolution when we start to develop granularity of the patterns. A big surprise that once the model actually comes to that, put it right station, potentially get it to this. I think Marty will see a little bit more to Dave in his talk. So making data and keeping that in an absolute model is very complex and requires observation.
Thank you so much. Very impressive. And I just want to follow up on the question being asked just now. I'm a hydrologist. My name is Lee, and work at Silver. So for most hydrologists, we have like three or maybe four buckets in our system, right? Snowpack, with surface storm water and in the rock, groundwater, maybe plus lakes and rivers. And among them, snow is a very efficient water keeper. And because it's cold, so number one is the inner barrier, is going to use the water atmosphere. So you can melt every gram of water in 80 calories. So that adds to the 500 calories of evaporation. Number two, once the rain goes in the soil, there are a few things. Number one, less energy barrier. Number two is more surface area because we evaporate through the plants, a lot of air evaporate. And also number three, keep water for a much longer time than one climate. And so, especially in Western US, the evaporation amount is very high. So the transition from one bucket to another has a huge impact.
I just never really had a good number in my head for how much sublimation is there. Meaning you're going straight essentially from the ice to the vapor and the cold, dry winds get the super strong sound. It seems like it could be a good number. You have experience that or the numbers.
Yeah, that's a great question. I don't. I think that's one of the places where snow hydrologists usually some more time. But in NPR, it's Colorado's definitely a place that we study. We lose a lot of water separation. I was working in Saskatchewan as a postdoc, and that's a place where I learned the value and the importance of sublimation. How quickly snow disappears in a dry day. On models to really represent that to get those.
You put an order of magnitude guess.
Yes, so one of the things is that the trees are really efficient sublimating forests that hold snow up in the air. There's a lot of surface area, there's a lot of wind exposure. You can lose over 50% in some studies to sublimation from what is on the planet itself. That's
I have a question for you. I really love that framework and deep convergence that you presented. So I was wondering, what are the disciplines that you're excited or looking to collaborate with? Who do you think you need to bring in to the conversation?
Yeah, thanks. Some of the influence that I'm driving to work with are social scientists. And again, how best to network and to provide actionable, usable, just kind of data, including water resource data, as well as indigenous and community populations, and native tribes, First Nations. In many cases, they have a better understanding of the physical system than I do, just from oral history that can pass down years. So every time I sit down with indigenous communities,
We're going to move on to our next panelists now, but we will have time at the end of the session for more questions to the whole group. So if you have questions, you can write those down and we'll get a chance to ask them. Okay, so next we have a virtual presentation from Dr. Michael Dettinger. Mike is currently a visiting researcher at the Scripps Institution of Oceanography, working at the Center for Western Weather and Water Extremes. But he's coming from a 38-year career at USGS, where he produced a really enormous body of research around climate variability, extreme precipitation, climate change adaptation. So I always learn something new every time I hear from Mike. Really excited to have him be part of the panel. So I think he's all set up. Is he controlling his own slides? Okay. All right, Mike, take it away.
Okay, can you see my slides?
Yes. And your audio is good.
Okay, thanks. So what what I wanted to do today, this kind of grew out of a conversation I had with some of the organizers about wanting to be there and wanting to have a side meeting to just talk about the distant future of monitoring in the interior West, largely because I see actions going on recently to expand our existing networks. And I just wanted to return to some work that Marty and I did about a dozen years ago. We were invited to by the Western States Water Council to put together a vision of what monitoring for water and extreme precipitation and flooding and the like could look like for the Western region. This resulted in the paper that's referenced down in the lower right here in 2014, and a couple of position statements from the Western States Water Council that kind of bought into and at least gave their moral support to the development of this network. But that's a dozen years ago, and we're talking again about expanding our networks in the West. Marty's going to be talking about changes to the soil moisture monitoring and the like. And it just seemed to me that we should keep the long view in mind as we did the hard work of developing the short-term improvements to our monitoring. The first step in putting together that vision was to acknowledge and recognize that atmospheric rivers, which are an enormous importance on the West Coast, were important within the interior, but not the only thing going on in the interior. And so we, looked around a bit, and basically this cartoon, the big map here is a cartoon showing different ways that we get our largest storms and storm impacts in the West. And atmospheric rivers are certainly there, but the monsoon, of course, is a big thing to pay attention to on the Front Range and in the Rockies near you. Upslope storms are a big deal, and so on. And as Keith mentioned, we really have to pay attention to snow melt That's a big driver of large flows and floods and all of our water resources. And as you put that story together of all the different ways that we get our big storms and big water for resources and the like, principal conclusion that we came to early on was that vapor transports are really the key to all of this. This slide shows for monsoons, the notion that, well, monsoons are fed by an influx of vapor from the summertime influxes of vapor from the more or less from the south. Upslopes are all about getting that twist of atmospheric circulation that brings cold, moist winds up into the Rockies. And then, of course, atmospheric rivers are about these narrow bands of intense water vapor transport. And so, point number one, we really need to understand water vapor a bit more than we do. And well, this slide, the big map shows a vision from John Rutz in Salt Lake City of the penetration of atmospheric rivers into the interior West. And you can see it coming. These are primary pathways of penetration of the atmospheric rivers. In between these, for instance, over central Nevada there, there really are dead zones for the penetration of atmospheric rivers. In essence, those are the rain shadows that make some of our most intense deserts and the like. Anyway, and I show over here on the left a couple maps from December 2010, and the one on the top is showing the vapor transports from a particular storm. And I put this one up here because it's a storm that really penetrated all the way up to the Yampa Basin. And on that one, the warmer colors are the more intense. The zones in which the vapor transport is more intense. There's more vapor being pushed along that atmospheric river. And then on the bottom are the precipitation that resulted from it. And again, you can see that it reaches all the way up into the Yampa Basin. And so these things reach far inland. Keith mentioned the work by Jessica Lundquist and others, basically arguing that our models have now surpassed our ability to observe. And I would just say that's not necessarily the biggest ringing endorsement of our models, although I'm not going to argue that right here. But it's really a sad state of affairs for our observations. And I would just note that that's an important point, because this is what I would argue, pretty much our only wall-to-wall coverage vision observations of these atmospheric rivers and major vapor transports looks like. And it's not a artistic license to have the Southwest here, Southwestern US and Mexico in black. Our satellite imaging of these vapors simply doesn't work over the land surfaces. And so what we directly see of these vapor transports, specifically here for atmospheric rivers, is over the ocean. And then once we get over land, it starts to be very point by point if there happens to be some very specialized observations being made at any given point. And we no longer have the big picture, arguably. Okay, so with that background, let's go back to this business of visioning a really 21st century network of monitoring for the interior West. This image, this figure here comes from, from a chapter by Marty in our Atmospheric Rivers book, but it basically represents a tiered vision that we used in California to design and actually implement what we were calling a 21st century observation network for California. The way it works is the lower end, the tier 1 down there are the relatively inexpensive and relatively we understand how to make these measurements and most often where to make these measurements and the like. Tier 2 are technologies that exist, but they're a bit more expensive, and frankly, deployment of them, figuring out where to put them, sometimes requires a bit more study before you necessarily want to invest. Third tier are technologies that are the ones listed here are pretty much available, and we have much less experience with them. And we're really learning how to do those still, and they are more expensive. And then finally, the top tier, which in this case, we tend to point at offshore reconnaissance flights and the like for looking at our atmospheric rivers. That gets really pricey. And we're a lot further along now in how to do it and actually doing it in a operational mode rather than the research mode these days, but that becomes the highest tier. So what we were talking about, and this was for California that we did this, was thinking about monitoring in terms of not just what we can do right now and not just expansion of our existing networks, but what we want to be doing and what we need to be doing in the future, even beyond what we could do right now. Let me see. So this is what we ended up putting together. This exists, our 21st century storm observing network for California. It was an effort funded and worked on by both California's Department of Water Resources and NOAA, with some help from us at Scripps as part of the brain trust rather than the money trust. And we ended up, we have actually implemented a network that, as you can see here in the lower right, about 43 different soil moisture sites scattered around the state, 37 of these things called GPS vapor that I'll show you on the next slide, 10 snow of these other things called snow level radars that were developed specifically for this use. And I'll talk to you a little bit about those on the next slide. And finally, 5 of the major atmospheric river observatories that I'll describe briefly in a little bit. Okay, so this is actually, in my view, the most important slide of this talk. And let me just run through the words, and then let's look at those maps, because the maps are the most important thing here. So this was really tier 1. This is the easy stuff. And we developed, we located some 40 plus sites around the state that were at mid to, actually these were scattered all through the various altitude zones in California. This is a technology that was really difficult, I can tell you from experience, 15 or 20 years ago and earlier. Really difficult and really expensive. And these days it's really, it's come down in price. It's very doable. So it's the fact that we didn't have a great soil moisture network in California was largely an artifact of the fact that 20 years ago, it was just too expensive and too hard. I mean, it was something that had to stay around and tend by hand most of the time. Snow level radars were another element in the first tier, and we have had 10 of those that we put in California. And this was actually a former radar, upward looking radar. The funny looking caisson things over there in the middle left are these snow level radars. And what they are is taking upward looking radar profilers that can cost $500,000 and stripping them down to say, we don't need all of that information everywhere. What we do need very often is to know exactly in real time where the snow level is, because that has everything to do with flooding and how much water ends up sticking in the snow and the like. And the guys in Marty's shop at NOAA in those days stripped down some very expensive radar technology that I'll show you on the next slide, down to where these came in, instead of $500,000, we brought it down by a factor of 10 or more. He brought it down by a factor of 10 or more. And so suddenly these were quite doable, and we did it, that we were able to put them out. Finally, on the bottom here in the left is GPS vapor. And this is basically a high-end GPS antenna like the one in your phone, but a high-end version of that we can use to directly and in real time monitor how much water vapor is directly overhead, in great detail. You can see there that we put in about 45 of these in California. Returning to the maps, I'll just say, the soil moisture one, the dots are pretty small. This is from the US National Soil Moisture Database. And so a lot of dots you're not necessarily seeing on the screen, but what you will see, I hope, is that there's an enormous gap between the Tahoe area in California, in the Sierra, and then the Wasatch Front, you start to see some more. And then finally in the Rockies, up in parts of the Rockies, you see them. But the interior West is just almost devoid of these things compared to, say, California or the Rockies over here, over where you guys are at. Snow level radar, similarly, basically, we've got a bunch of those on the West Coast now. And then it just drops off. There's one in Dugway over by Salt Lake City. And then finally, GPS vapor is a cheaper and kind of easier in many ways, technology to deploy and use. But again, major gap. Numbers drop off remarkably in the interior West. And, I've worked in the West my whole life. And, so I'm used to not having as much data as everyone else does, put it that way, many data sites. But I believe that we need to be, working to fill in these gaps, and we need to be asking really loud for more coverage to bring our observation networks up to the level of density of most of the country, frankly. Anyway, tier 2 was that more expensive stuff, and primary candidate there was the basically what we in California called the atmospheric river observatories. I would say for the interior West, let's just call them vapor transport observatories. At one of these, you're looking at a whole raft of different monitoring systems, wind profilers, acoustic ones, and radar, upward-looking radar, and expensive distrometers that measure the size and fall speed of precipitation, and so on. Basically, this is how we could, if we had some of these out here in California, we were absolutely over the moon when we got to a point where we had 5 of these along the California coast. There's now at least a couple more up further north on the West Coast. So that gives you a sense of how many you might need. These aren't something that you need at hundreds and hundreds of places. You couldn't afford it, and there aren't enough people to run them. But this is the way that you actually track that key water vapor transport that I mentioned earlier on. What's going on here? Okay, there we go. And then let me just, I would like to pile on some of what Keith was talking about. And basically our other point was that, that we've got a really pretty great SNOTEL network, snow monitoring network in the West. Largely almost, well, what would it be? 3/4 or something like that, or more maybe, from the Natural Resources Conservation Service, the USDA, and then a bunch from various operations in California, which likes to do its own thing. But this, I would just argue, and here's my cantankerous coming out. I would just argue that our SNOTEL network is wonderful. It's amazing, but it's designed for its original purpose, which was for water supply, forecasting purposes for water supply. And we are well into, we're 20 years into the 21st century. We are well into the Anthropocene. And there are just lots more things that we really need to be tracking in terms of our Western snow. I've got a list there in white up towards the top there. Dust on snow, we know, has everything to do with accelerating snowmelt and the like. Rain on snow, as Keith was talking about, enhanced ET, evaporative demands, that Chuck was referring to, aerosols, loss of water into the soil moisture, never to be seen again, and is an increasingly scary thing that we're dealing with. And so, what we would suggest is to revisit the SNOTEL network and actually beyond the SNOTEL network, but start with the SNOTEL network and actually start to think about other things that we need to know that aren't, in quotes, design or just water supply. And I'm a water supply guy, so I say that with big quotes around it, but not just water supply, not just warming induced climate change, hydrologic change, but we've got a whole raft of changes coming our way. And over here on the right, we listed a number of different kinds of monitoring that we think should be done, or at least planned for, including some that we just don't know how to do, quite frankly, now of the character of the offshore monitoring reconnaissance. When we were laying out this network, we've learned in that subsequent 20 years really how to do that, and now it's operational. And that all led us to this particular vision. We weren't really constrained too much by money or much, but just what would we like if we really were allowed to build out things. And this was a group of I think about 24, I didn't count recently, but about 24 scientists from around the West, who are interested in the West. And we came up with this really ambitious list. And you can see, we talked about 100 new low to mid altitude soil moisture sites. Why not high altitude? Well, that's because the NRCS has indeed put in, has soil moisture up at most, as far as I know, all of the SNOTELs these days. And so the high altitude is reasonably well covered with soil moisture, but down below, we don't have the NRCS putting these monitoring systems in. Previous slide, I talked about augmenting SNOTEL sites to really begin to address problems that go beyond or are different from purely water supply. Those GPS water vapor sites, you saw the gap in the map earlier. We need to just fill in so that we have a much better sense of where the water vapor is going in these concentrated streams, whether they be ARs or monsoon or whatever. The snow level, well, you can see snow level radars, AR observatories or their equivalents provide the only way I believe that we're really going to be able to know with some confidence how these water vapor transports are actually making their way through and around and over the mountains. Right now, we know that on the basis of models. It's pretty much that's the situation. All we know is what the models tell us, and that's a somewhat precarious position to be in, because our models are, well, we won't know when our models are failing until we get some observations out there. And then, and then gap filling radars, which we haven't talked about, but are basically how you make our weather radars that you're used to seeing on the news and the like work in a mountainous countryside. So this is my wrap up. And it basically, here's the story I've been trying to tell you, the visioning process I've been trying to tell you, that we basically identified vapor transport as a key gap in our current monitoring. We need some sort of observatories for those. Enhancements to the storm, snow, and stream flow monitoring to provide more than just the historical water supply focus. There are lots of other things that we're using these networks to infer and to sort out, but let's redesign them or augment those networks to actually make it not just we're backing into these other answers to these other problems based on data systems that were designed for something other else, which is to say designed for water supply purposes. The offshore monitoring was a key part of our vision, and that's really coming together rapidly, and it's now operational. I think that Marty's going to talk about that a little bit. And ultimately, that leads us to broad monitoring of key atmospheric conditions that are going to fuel water supply and floods in a warming and otherwise changing world. So I had a question for you guys, and it's difficult remotely to pull this off, but my question is, it's a dozen years later, what would you think that we need? We identified some problems that we thought were particularly important and some gaps and that sort of thing. But, what do you think, kind of in the absence of the immediate question, how would you pay for this the next year? In the absence of that question, what are the things that you would really like to see, that you think to see? What are the problems you think we need to be observing to address? Anyway, I'm trying to toss this back in your laps. So if there's any time for discussion, I would really love to hear what you think I don't know if ideal is quite the word, but the ideal monitoring for the interior West would look like going forward. And that's with that, I toss it back.
That sounds good. Okay, great. Thank you so much, Mike. That was fantastic. And I love that you gave us all a prompt to discuss during the Q&A session and maybe into lunch and into the afternoon. We're going to move right into our next panelist presentation. And so hold any questions that you have for Mike until our full panel Q&A. So our final panelist for this session is Dr. Marty Ralph. Marty is the founder and director of the Center for Western Weather and Water Extremes at Scripps Institution of Oceanography. He spent his first phase of his career, 21 years at NOAA, before leaving to found the center to really focus on these needs of monitoring and improving forecasts in the West. And I like that Mike made that point very clear that a lot of other places in the country have much denser networks, much more investment into having this type of data and information. And so Marty's been a really big driver in trying to solve that problem in California, and then now expanding eastward into the rest of the West. So Marty and I get to work together on forecast informed reservoir operations, which is just such an exciting program, and his leadership there has been so monumental to scaling up and really being able to deliver solutions to water supply needs in California. So I will bring Marty up here for our final discussion, and then we'll have a bigger Q&A.
Wonderful to be here. Can you hear me okay? Mike Dettinger and Keith Musselman gave great presentations. I have the benefit of building on those, and thanks for sharing those ahead of the meeting so I could be aware of what you were talking about, and apologies for not getting mine in until this morning. But I wanted to create a particular slide, and it's in there, and I'll tell you which one it is when we get there. The title of the talk I switched at the last minute as well. I was going to talk initially purely about the soil moisture network concept that we've been building for the last couple of years, and in fact introduced the idea here at the last rendezvous last September. So there might be a couple slides you may recognize there. So I'm going to read the title word for word because it's exactly what I want to do. 2 opportunities to improve support for water management in the Upper Colorado Basin. New spring precipitation forecasts. I'm just going to plant the seed of an idea there, not really show results yet, but there's a path there that I think we could pursue. And soil moisture observations. This is like back in the day, it's a shovel-ready thing. It's a matter of investment being needed, and I think we can really move the needle on that pretty quickly. Okay. I don't really need to familiarize you with the basin, but I do want to highlight this time series of the water levels at Lake Powell over the 5 years from 2017 or 4 or 5 years, 2017 to 2021. And in particular, you can see the decrease over 4 years of more than about half of the total water in the reservoir as of September, over those 4 years was lost. I learned the term depletion today from Chuck Cullum's talk and understand that is a really sensible term. And then, so the question is what just happened this year? Well, it's off the chart from last year anyways to an even lower level, down by another substantial amount. And that means that in total, the water volume in Lake Powell in early September in 5 years has decreased by 60%. So, it doesn't take a rocket scientist to figure out, it's like your bank account, right? You can't keep going spending like that. So something's got to change. What we're going to be talking about here isn't so much about how to make decisions about water management, but what information could we in the science and engineering worlds generate, new information that could help quantify what might Mother Nature provide. And I'll share a few ideas about that in just a moment. And before doing so, though, I want to highlight how challenging it is to make these predictions and how the National Weather Service does an incredible job of covering a wide variety of topics, a huge number of stakeholders in different fields, from transportation to agriculture to water management to coastal management, that they provide the foundation for a lot of what the decisions are, and they have a super tough job. And part of the idea of this work I'll share here is that we're trying to innovate in ways that could help people like the National Weather Service have more information available to use for others who are also generating forecasts to have it available for themselves, like we heard from Andy Rossi this morning. Alrighty, so the challenge is that it's so important to know ahead of time how much snowpack there's going to be and how much really runoff there's going to be. And this table, very simple table, highlights that in March sometime, usually early March, there's a forecast made of how much the total runoff or inflow into Lake Powell will be. And here you can see that back in 2018, that forecast was really pretty good. It was just within 9%, it was a little bit low. Then the next year, it turned out to be 37. What happened was 37% more inflow than had been predicted. super hard to get that right. If you got huge burst of stormy weather in the spring, you know, and you haven't predicted that and you're making a forecast in March, that's really hard to do. Probably one of these cases where not having a good sense of what the precipitation is going to be is very, makes it even more difficult. The next year, however, was 23% lower than what was observed in inflow was 23% lower than predicted. So a bit too optimistic. Same with the next year. And I presented this slide last year and wondered, you know, how did it go this year? And thanks to Rob Hartman for, you know, finding the numbers here. It was about 15% lower in reality than what was predicted. So we see, you know, it's only 5 years and you can't really detect this trend with that. But my sense in talking with folks in water management that there's this sense that we've been too optimistic in the runoff projections in the spring of what's going to end up coming into Powell, and that it's a little bit more than just a small sample size thing. There's something serious going on in the watershed. So another part of the equation, though, is this precipitation, and I want to highlight that here in a very simple diagram. This is from a very nice report. I forget, it was 2020, I think, and it's for the Upper Colorado from there's a particular watershed stream gauge. It's like on the border, I think, between Utah and Colorado, where the Colorado River flows out. And what it shows is the you know 10%, 30%, 50%, 70%, 90%, and max and min values historically averaged over many years, and 3 examples of specific years in there. But I want to highlight a particularly important point. If you look at in late March there, you can see on the left vertical line there, the dry year there is peaking. We got a 2002 example, you know, in late March. And then you got the 2011 case, which peaked in early May. And if you look at the variation there, just step back from it and think, you're there trying to make a forecast in early March or mid-March of what's going to be the runoff for the year. And look what can happen after that in this big area. You could either deplete there's no more growth in the snowpack. It's gone. It just disappears. Versus you get twice as much snowpack as you had at the beginning of your forecast. That is a challenge. I'm a precipitation guy. That's sort of my background. How the heck are we going to get that right? That is super hard to do. We have a hard time predicting a few days out what the precipitation is going to be. And here we've got a several week period that is almost like the vital decider, you know, for the water inflow into Lake Powell. And it's a tough nut to crack, but I want to show you a little bit of hope. I think there's a direction we could take to help with that. So next, I want to just highlight that you know, what causes errors in the forecast of those 6 weeks is really spring precipitation might very well be the biggest driver. And in terms of snowpack, that's the key thing. But if we think also about runoff and inflow, we've heard about from Chuck and others how soil moisture can moderate or modulate how much runoff from the snowpack gets into the rivers. It's not the only parameter that influences it, but it's a little bit like the bucket thing Ming was mentioning. You dry out that bucket too much the previous year, you're going to pay the cost to refill that before you're going to get as much water in the river in the spring. So soil moisture deficit is another parameter. And I think of that, by the way, as almost like another reservoir in our landscape. It's just one we don't see. It's underground. And yet we know intuitively that if you've got it super dry at the beginning of the snowmelt season, you're just not going to get as much water in the rivers as you would if you had a super wet soil going into the winter. All right. And then the other is sublimation, hence my question for Keith earlier. And I see this as sort of asterisk on that one. I think that's super hard. It's a little bit beyond. I'm not going to talk about that from here on, but that needs to be worked on. It's a big term potentially, as Keith mentioned. All right, so let me just point out one thing here in that black line. This is for the tower tower SNOTEL. And by the way, thank goodness for NRCS and the SNOTEL network. We'd hardly have an opportunity to do a lot of what we need to do without that. So great work by NRCS, and I hope that the resources and funding that they need to be effective can grow so they can succeed as well. So this black line is the up to earlier this year, it was the snow accumulation at the tower site right above town here. And look at that big jump I've circled. That was massive. Let's take a look at that for a moment. And just eyeball for a second, you know, how much a jump that was. In the left vertical axis, you go 20 to 30 inches. It was like an 8-inch snow water equivalent jump in a very short period of time. We'll you know, dive into that in just a moment. Then look at the, I guess the green line is sort of the average. Let me go back one. I'm sorry. The green line is the average total, which is up, you know, towards 50. So you can just very simply recognize that that 8 inches compared to the 50 normal max, it's like 20%, fell in a couple days. So that's sort of the story of my career in the West in precipitation, is starting to recognize more and more that these singular events can make or break the water year. And this is super true in Northern California. The headwaters of the State Water Project and the Central Valley Project, it's vital for ag in California, vital for Southern California cities, is that, and this was work from Mike Dettinger and Dan Cahan. If you look at the curve over a century of annual precipitation in the big watershed of Northern California, the Sierras and Shasta and all that, imagine a curve that goes up and down the drought and flood years. If you take the 5% wettest days each year and put those days in a different bucket for counting and keep the other 95% of the wet days, and you look at how the total precipitation from those 95% of the other wet days varies from year to year, it explains 15% of the variance in interannual precipitation. 15%, it's almost irrelevant. It's as if we can count on those sort of run-of-the-mill storms. Those top 5% wettest days, how they vary from year to year, determines 85% of the variance in annual precipitation. Those days are literally what determine drought or flood, just a few days each year. I don't think it's quite as extreme here in the upper Colorado than that. You got more pathways and approaches, but that concept is still applicable in some way. It's just to what degree. And this case is a case in point. So let me dig into that for just a moment. Here's an example that we're, let's say, take the 4 days that are circled there. And there's the first two I mentioned, number 1 and 2, and they added up to 14.3% of that 50-inch per year, you know, sort of total average for the Tower Snowtell. And then the other two, when you add up, they're another 8% or so. So we're up to 22% of the total average for the year. And I should have updated this with what the actual total was. Anybody remember what the total max was this year for Tower? We don't have enough water nerds in here, I guess. So I think it was about normal by the time we got to the end, maybe 90%. So this was probably a quarter of the total snowpack for the year accumulated in four days and 3 different storms. Well, let's look at the most intense one there. I'll skip that. Let's look at this one for a moment and see what kind of storm that was. And I want to thank Dr. Zhenhai Zhang and my group for the analysis here. What we found is, well, it was an atmospheric river that penetrated inland. If you remember Mike's talk, there were some of these big vectors, you know, pointing across the landscape, penetrating through the big mountain ranges. Well, in this case, it just overwhelmed all the mountain ranges and came right in through the northwest. On the upper left here, you can see, I guess I can't do the pointer. You can see the northwest coast, the pink coming in there. This is the vapor transport, the integrated vapor transport, IVT, accumulated over 48 hours. So we time integrate, we call it. And those are massive amounts of water vapor coming in. And look how it's pointed with the arrows. That's the direction of the transport, straight into the Tower Snowtell site. If you go back to the west a little bit, the very northeast corner of the panhandle of Utah, there's a Snowtell site up there that had almost the same amount in 2 days. I think this was the wettest 2-day period on record at the Tower site, as it was for that other site as well. And there's a whole, if you go back to the Snowtell sites, going back to the northwest, you'll see that like just big pulse of snow water equivalent contribution. And then on the right-hand panel, you see the anomaly compared to normal vapor transport. It's more than, that pink is more than 2.5 times normal. This is a massive anomaly. This is a big AR. It caused problems in the Pacific Northwest with heavy rain and flooding, and it penetrated into here and dumped, you know, something on the order of, what was it, 8 out of 50. So, you know, 15%, call it, of the season's, you know, snowpack in 2 days. Well, that was an atmospheric river. And I want to show an example here of, this is more just really as a case in point, and when we in science and forecasting pour the coals to trying to solve a serious societal problem, we can really move the needle. And by the way, before I left NOAA to come to Scripps, I had led a program that invested in innovation for a variety of other phenomena, including thunderstorms and hurricanes and the like. And not just the stuff I led, but over 20 years, the nation made massive strides in improving the prediction of hurricanes. And I was involved early on in some of the planning about what to do to achieve that, and big effort by the broader science community of meteorology, by the National Weather Service, NSF, NASA, all sorts of agencies involved. It transformed hurricane prediction and improved the track forecast and now the intensity forecast dramatically. So the point here I'm trying to make is that we're now taking that kind of focus and trying to identify what in the West do we need to focus on that we could actually move the needle on. It doesn't happen overnight. It's like a decade, 2 decades, but if you don't start, you don't get to the end. So in the West, it's these atmospheric rivers. They are really a dominant thing in the Western US. 84% of all flood damages from FEMA over 40 years were from atmospheric river storms. You know, most of that happens on the populated West Coast, but 84%, think of that. It's more than $1 billion a year on average, and almost all of them are from ARs. And now, in order to achieve improvements in dealing with those problematic storms and to take advantage of better forecasts or try to improve forecasts for reservoir operations for water supply as well, which Alyssa mentioned, forecast informed reservoir operations. We started that as well. We realized that these AR storms are coming in off the ocean, and there's less observations of the weather over the oceans than over the land. So we need better observations over there. I won't go through all the science. There's like 25 journal articles that laid the foundation for this and have proven it out. But what we invented was one of the things in that big 4-panel diagram Mike Dettinger showed about offshore measurements. We've invented that now. We've flown 100 aircraft flights offshore in the last 3 years or so to collect data in atmospheric rivers, get it into the operational weather prediction models to make the West Coast forecast better for ARs. And this is a schematic of how we do it. And you see BAMS is the Bulletin of American Meteorological Society. It's a premier journal in meteorology. They chose our work as the cover in November last year. And on the inside cover, the first time they ever did a front cover and inside cover coordinated, this figure on the right, where you see schematics of the 2 aircraft. There's some extra satellite data we use, the buoys, which look like little fishing buoys. And the AR is that sort of blob there, color translucent thing. And those vertical dot lines are the dropsons. We release little sensor packages like 2 Coke cans in size, cardboard essentially, and a little bit of metal. Parachute, 20 minutes to get to the down, and it radios back the temperature, pressure, wind, and moisture. And we then send that into the data bucket that the whole world uses to draw from to run their numerical weather prediction models for global weather. And it has moved the needle on the biggest storms in the West Coast in the last couple of years by reducing the error in the forecast of precipitation by 50% at some lead times. Has taken the accuracy without these data at 2 days lead time. We now have that accuracy at 5 days lead time. And in the weather business, improving forecasts by 3 days lead time is hard to do. So I'm sharing this a bit because it's a success story of identifying a phenomena, a problem, making new observations, working with stakeholders who need the information, and figuring it out. And for a common language description of that, I'd like to encourage you to take a look at something I'm very proud of. We had a story in Scientific American. They invited it. They asked me to write it, and their graphic artist created this a little overly scary picture. And seriously, they wouldn't let me edit it at all. I just said, take the lightning out, take the lightning out. It's not a thing. They did take the lightning out, but it's still sort of sexy. And it's actually in this month's Scientific American Journal. So you can find it online or whatever. And the point of it being that topic has reached a level of public awareness. Congress is supporting it. The aircraft that are used for the missions that we fly, they already existed in the US arsenal of weather for hurricanes. There's like 10 of them. And I just said, well, let's use them in the winter. Just said there's a lot more to it than that. But, it basically, we're taking infrastructure that already exists and applying it in a new way. And this article tells the story of that, including the creation of a scale for ARs, which is on the right here. We have now like the hurricane scale. We have AR 1, 2, 3, 4, and 5. And then it also tells the story of how the information is influencing emergency managers and how it's being used by reservoir operators. So I would recommend that story as sort of a common language explanation of how all the science points to solutions that sometimes get implemented and can make a difference in the real world. With that context, I want to show you a vision very briefly of what I think could move the needle for water management in the West right now. And that tier 1, 2, 3, 4 pyramid thing that Mike showed, this is like tier 1. The technology exists. It's absolutely ready to go. It's commercially available. There are teams like mine who can deploy it very efficiently. We've done them before. We've deployed many of these over regions that need it. And we know how to get that data in real time back into tools that can then send it to water managers. And we put a site in the upper basin here, started running just recently. I want to really thank the team for doing that. Anna Wilson is the project manager on this from my group, super job leading it, along with Michelle Stewart and the Yampa Valley Sustainability Council's team, number of people involved, and then the Upper Yampa Water Conservation District, Andy Ross, you heard from this morning, sponsored it. So we've got a demo in there. So let me tell that story here. But I can't resist showing you the picture I told you I wanted to integrate into the talk this morning. I took a road trip this summer. I started taking pictures of dirt. I'm a meteorologist. What am I doing taking pictures of dirt? But it was road cuts. You know, you see this all the time. We drive around. Just think of the diversity of the soil, the rockiness of it, the granularity of it, how many plants are rooted in it, varies dramatically across our landscape. And that's one of the underlying principles of our vision for this network of soil moisture sensors, is that there's a lot going on in the landscape where the way water interacts with the soils varies dramatically. These were, by the way, from a number of them from Western Colorado. And all right, let me go into some details here. It's a little bit hard to see because I don't have the projection normal here. So the basic idea we developed a couple of years ago, and thanks to Andy Rossi and company, we've now deployed the first one. One of the key steps to do that, oh, and by the way, I mentioned that we've done something like this before. On the right, you can see a watershed in Northern California called the Russian River. It's actually about the same size as the Yampa, and we've deployed dozens and dozens of soil moisture sensors in that, and we've learned from that experience, and we're taking some of those lessons as we think about the vision for here. That middle diagram, super colorful, that's the Yampa Basin, the Yampa River Basin, and each color represents what we consider a cluster of similarly characterized soil conditions or landscape conditions. Either they're south facing or north facing, east facing, west facing. They're high alpine above tree line, they're montane with forests, they're grasslands, they're flat. There's several different characteristics that come into play in an analysis that was done objectively that said if we group those different kind of characteristics, or the characteristics of each grid cell in the Yampa Basin, we find that there's sort of 8 clusters total that are really distinct from one another. And we believe that those 8 clusters represent essentially the target for what we really need to sample well in order to have a good quantitative estimate of how much water there is in the soil in the basin as a whole. And of course, if you can see the diversity of how those different colors are distributed there, you know, one station for each color is probably not going to be enough either. Personally, I think 50 stations would be about right for the Upper Yampa, but to be conservative, we're recommending in our vision about 25 total for the Upper Yampa. In the areas, if you think of the hills out here, what a view, by the way. Where's that water that's going into the river coming from? It's coming from certain parts of the landscape. Some parts are more productive than others. We want to explore where that is and make sure we know what's in the soil, you know, for that. All right. So what does it look like? This is what the red star there is where we've got our demo site schematically, and then the yellow dots are where the other 25 would go. And you can see how they're sort of clustered in the slopes of the mountains there. I want to highlight also that the NRCS did implement a number of they have soil moisture sites at their high altitude SNOTEL locations. Thank goodness we've got those as a baseline. But imagine yourself hiking and seeing where those are at. They tend to be in places sometimes where there might actually be sort of a natural accumulation of water underground in a meadow, that sort of thing. Those might not be fully representative of this complex landscape of soil types and how soil moisture runs through it. So building on that NRCS baseline, we would add these sites in places that differ from those in ways that complement that very important network. And to carry out this project here, the team you see highlighted there at the top, a number of folks of whom are here. We really worked closely with Andy Rossi and with other experts in the area to ensure that we understood what their needs were. And we worked hard to do that analysis of what soil types were and to pick a place where we could actually get the site approval and get equipment in the ground. And it just got installed. And I want to show you the first data from that. Where is it? It's in the bottom right of that diagram. Sorry. There's a black dot in the bottom right there. Let me go. See it show up there. It's in the same basin, I think, that Andy showed as the headwaters of the Yampa River. It's the near the Yamcolo Reservoir, right? And that was the first site to do this as a demo. And here's the team installing it. And you see at the top there a Met Tower that has other instruments on it. It's the first thing we would do if all we did is put the soil moisture in, we'd ask, did it rain? So we've got a rain gauge up there, and we'll try to, and we'll have snow depth measurements, but also wind and temperature and pressure, because you got to have the data logger anyways and the data transmission. So we sort of used it as a basis for a more complete package. And you see the team there in the middle picture, and you can see the soil pit there. They got down to a meter depth for the lowest sensor, and that's our target. Is like basically 5 centimeters, 10 centimeters, 20, 50, and 100. Did I miss one? That's right. And that goes down essentially 40 inches, about this deep. And there's a lot that goes on there. And if it's done right, you can actually see when the rain hits, you can see it sort of penetrate over time down deeper into the soil. And let's see what happened in the last few days. There's a close-up of the sensors in the pit. Here in the top left, we see the case from just about a week ago. There was on the upper diagram, you see, go from left to right is one that's like a week. The blue bars are the 6-hourly precip. The red is the accumulation during that period. So about 0.6 inches fell at the site in those first 2 days. And the bottom panel there, each different colored line is a different depth. And you can see, for example, the red line, which is at 2 inches depth, went on the left, these big jumps up corresponding to the precipitation. That's certainly a good sign. The sensors are working. And then the orange line, which is at 4 inches, also showed those jumps. But then notice the green and yellow lines, they didn't really budge until after both pulses of rain had hit. That's how long it took for that wetting front, I think it's called, to get down to that level. And I don't know what's going on with the purple one at 40 inches. Maybe there's like cracks from it was just filled in and it's puddled a little bit down there or something. I don't know. And then the blue one there at 20 inches shows it hasn't really changed. So this is the kind of information we'll be collecting from this. And there's temperature in there as well. Soil temperature. So the idea is that this will become the beginning of a long-term baseline for measuring how soil moisture is evolving in this watershed, not only for potentially using it to help figure out, in the next spring snow melt, is the soil going to absorb more or less than normal of that melt before water gets into the river, but also from a climate change perspective. Imagine we had this type of data going back 40 years, like we have the SNOWTEL data. We might see a big change starting about 20 years ago. Now we can pretty much only guess. So 20 years from now, this site will ideally have produced data every day, and those kind of trends might appear. I'm going to be an optimist and say we're going to see a return to more wet, and we'll see some recovery there. But this is the example. Now, what does the fuller implementation looks like for the Upper Colorado in the whole? Thinking of the Chuck Column challenge and the challenges for the state that that we heard about as well this morning, that this would be basically 25 sites in each of these 6 major tributaries. And we could show this relative to the existing network of scan sites, that the red dots are largely sort of in the lower altitudes, like in the farmland, maybe even influenced by irrigation. And that was what we encountered in California, is the soil moisture sites that had already been in place were all there for ag. They didn't really tell us what the soil moisture was like in the natural landscape that generates, runoff and floods. The middle is the snow-tell sites, and then the right, you can see all of them combined with our little yellow dots. So we're basically trying to fill in large areas of the landscape with that complex soil characterization I showed with the photographs, et cetera. So I'm going to close with that and a photo from Canyonlands last July that I really loved. And my contact information is here if you have any, I want to be in touch at all. So thank you.
Okay, so now we have about 20 minutes for Q&A. Since one of our panelists, Mike Dettinger, is online here, he can't hear questions unless they're spoken close to the laptop. So if you have a question, I would appreciate it if you could come up and ask it here, or if you'd rather, you can say your question from your chair and I'll restate it where Mike can hear it. Okay, so we'll open it up for general questions from the group for any of our 3 panelists or all of our panelists. There's one in the back here. Okay, thank you. Coming up.
My name is Kim, and my question is about the increased rain on snow events and increased spatial scale. Is there any relationship to land use change within that study? Or is there need for that to be studied?
Okay. Sure. Right.
Sure. Yeah, thanks for that question. It's a good one. It's not something that I've thought a lot about. I think that, as we see winter rains extending higher up in our elevations and covering more of our mountains, it certainly overlaps, new terrain. I think that's a nice way to put it anyway. But that means extending up into alpine terrain. You're extending up into timber industry in many parts of the country, and therefore you have different interactions between the precipitation and the runoff and the land cover. It's a good question. I haven't thought much about it.
Yeah, I think that provides an opportunity for that interdisciplinary collaboration that Keith was talking about during his notes as well, that land use change, human geography, study of that can really inform some of these models. Okay, yeah, coming up. Thank you.
John here. When you have your ocean buoys, are you measuring how deep are you measuring the temperature and salinity in the column below the buoy to see if there's a warm layer preventing upwelling or a cold layer, etc.? Because it has a big impact on the water content of the water vapor that's coming in on your atmospheric rivers.
Good question. And I didn't really speak to the ocean buoys very much. The ones that we're using for this purpose of weather prediction are drifting buoys that are really just taking measurements at the surface of sea surface temperature, currents, and we add sea level pressure to them through our program because the sea level pressure, when they carry it, really adds to the impact in the forecasting. The other points you made about ocean conditions are really important, and the ocean sea surface conditions in general really impact the weather, especially on longer time scales, where it is the major source, obviously, for the water vapor. there's a whole nother system called Argo floats. There's now 4,000 or 5,000 of them in the world's oceans. Scripps Oceanography was one of the innovation centers that invented those and deploys them. And they super cool. They descend down to a couple kilometers, measuring salinity and temperature and all that. And then they rise back up, pop out of the water for a little bit, transmit, then go back and do it again. And they drift slowly with the current. And those have really revolutionized oceanography and our understanding of how heat transfer occurs vertically. So one of the goals personally of moving to Scripps Oceanography was because of the importance of the ocean in modulating weather. And really appreciate your point. I don't have any better answers for you than that, but we're using the drifting buoys for the airborne, or for the atmospheric river reconnaissance program, with sea level pressure as the primary variable.
Do you want to come up here? Or?
No.
No. Okay.
I'm just wondering, the data we're putting together, how much of that data in California has been passed on to forest managers and wildfire managers to define where we should be planting trees in for the future forests and where we need to be fighting for that vegetation to help us out with wildland engineering and conservation?
Yeah, a good question. And Mike Dettinger, can you hear me?
Yeah, I can hear you.
I think you might be in a better position to take that question than I can. I think it was mostly about the land-based network that we had created that Mike showed, or about the over ocean stuff. All of it? Yeah.
What was, I'm sorry, I couldn't hear the question, so.
Yeah, I'll repeat the question. It was about, I think, use of the observations, whether they're the ground-based network that we've developed or the over ocean atmospheric river reconnaissance program, how they're being used by others who manage landscapes and the environment. And is that a fair phrase? Future forests. Okay.
Yeah.
So Mike, you want to take a crack at that?
It's always hard to really nail that down. I know, Marty, you can certainly talk about how the offshore reconnaissance, you guys can follow it directly into the weather models and the like. An awful lot of that data on the land, and that we've collected in California, is now making its way into what's called CDEC, California. CDEC. Yeah. Anyway, it's their
Data Exchange Center, I think.
There you go. Yeah. The catch is that the CDEC gets, visited and data downloaded or visualized on it by, thousands of people every day come winter, when we're all worrying about floods and our water supplies and all that. But it's really difficult to know exactly how it ends up thereafter being used. So I don't have a good answer for that. Sorry.
The one I could speak to is that from a wildfire standpoint, the soil moisture is important as a parameter. There are a lot of other parameters that are important, but we're starting to work with energy companies who are trying to estimate when the fire risk is high, and they're doing public safety power shutoffs now ahead of a situation that's super risky. So those kind of data can feed into that. From a forest health standpoint, I'm not familiar with any specific efforts, but the airborne reconnaissance program is improving forecasts of the precipitation that I imagine might be helpful in some manner. Just don't know the connections.
Yeah, I will just toss in that one of the things to realize about these kinds of networks and network enhancements is that the first few years you have to be really high-end analysts to figure out perhaps what's going on. But as time goes on and you get, a decade or two, now you can start to say things about, the data becomes more and more useful because you can put it in its historical context. And we're at around 10 to 12 years into the California experience. And so we're seeing some studies come out now that are directly using it to look for trends or for particular conditions under which you get, really good or bad forecasts of snow line and that sort of thing.
Thanks, Mike. I would just add to that, that forest management has really big implications on our water. I think we all know that. We have, in some cases, overly dense forests from over a century of fire suppression. Overly dense forests, like I mentioned with the sublimation question, can actually be a net loss to our system of water, as well as over competition from ET, or transpiration of those plants themselves. So I think the observations could be more helpful to understand that give and take. So an open forest, like you might see in a place that burns regularly, can accumulate more snow. But at the same time, you have this optimized, almost a natural optimization of the shading. That snow then sticks around for longer. That means the fuel moisture stays wetter for longer into the summer, and is a natural regulation of drought. But understanding how we use management to replicate that natural cycle is challenging. Our snow test stations are all in the open. None of them are underneath the forest. So we need improved understanding of the forest. And I think Jeff Deems with the Airborne Snow Observatory tomorrow is going to speak to the ability of ASO to map snow underneath the forests. Working together with forest managers with data like that, I think that would be the future to understand the convergence. Yeah, thanks.
And I think that question gets at something we have an opportunity to do here, which is talk to the water management and user community, the conservation community, about what type of data and information would be useful to you guys. And then that can inform the research and the development of these observational networks. And Mike had asked this group during his presentation, what would be the ideal network of observational data collection? So I wanted to ask if anybody, when Mike was posing that question, if you had an answer, or something you wanted to share that might then inform the research community. Mm-hmm. I don't think he can hear you from over there. If you want to come up, or we can restate. Thank you.
Mike, can you hear me now?
Yes, I can.
Okay, great. This is Gannett Haller. I'm a professor at the University of Utah, and I direct Storm Peak Laboratory. And our group studies extreme aerosol events. So looking at extreme dust storms and increases of aerosols pertaining to wildfires across the Western United States. And one thing that I think is a low-hanging fruit that I would advocate for is there's something called the Improved Network, which measures aerosols PM 2.5 and PM 10 in wilderness areas, class 1 wilderness areas across the United States. And currently they collect the PM 10 filters, which would be most useful for studies of dust, but they don't do a chemical analysis on those filters. So I think that's a really low-hanging fruit that could be advocated for, that would enhance our understanding of dust, specifically on snow and in snow-covered regions.
Thank you.
Thank you.
Thank you so much. I'm sorry, I couldn't even see people. Sorry for my voting challenge. I have to sit here. Yeah, Lynn Tan from the city of the it's really a sort of informative, inspiring session today. Yeah. And just to sort of my response to Mike's question, and given what I heard, sort of the inspiring things I heard from Keith, from Mike, and from Marty, my feeling is that if we can sort of target the problem in the most specific area, and to me, one of them would be the sort of a transitional area, as sort of Mike and Keith put in as a low to mid altitude. That's probably where a lot of snow may exist in shorter time periods in the year, probably more transitional zone where you probably don't get a whole season of snow. Sometimes you probably get no snow over certain, super dry years. But I think if we can target those areas to understand the change, how water get, switch from a sort of snow pan bucket to a stormwater bucket, and we can measure, say, both. When it's there's no snow, there's stormwater, there's no, there's snow. So that's just my point. Thank you.
Thanks, Dean. So in the first panel, it was Kelly who made the point, you can't manage what you don't measure, right? And so we heard from 3 speakers with really comprehensive proposals for how to better manage or measure the system so that it can be managed. So I want to give you each an opportunity to close out, 1 or 2 sentences or the takeaways that you want this group to be mulling over at lunch and talking about, and maybe keep that in mind, that we're providing information that can improve operations, and what's that connective tissue, how is that information actually informing actions that can improve drought conditions. So I'll start with Martin.
Thank you. I'll just say, I think the Yampa Basin is a remarkable place to find things. It's remarkable in so many ways, including the natural state of its landscape, the sense of community here, of people coming together to try to solve problems, understand things. I remember last year's rendezvous, those traits were described by leaders in Colorado Water. The collaborative nature of the community and the information really effective to try to do things out. And we couldn't be more happy to be here and find these things out.
Thank you.
I'm not sure I can say anything much better than that. I think that the one thing that I tell my students when we talk about future projections and stuff like that, while we Colorado, that we're quite discussion. But we're really as a result of our elevation. And in this case, in the other case, we're resilient because of the military watershed. And I think that serves as an indication of that we can make and advocate for policy decisions that have impact and can really turn things around for us. There are other communities that are not as fortunate, other parts of the country that are fortunate, certainly the globe. So I think that there's I'm just kind of filled with hope, looking at this community that kind of landscape here that we can preserve.
Thank you. Okay, Mike, you want to give us a closeout before we adjourn to lunch?
It's not much of a closeout. I was just going to say that I will, I'm going to be making a really big effort to be there in the flesh next year.